The red supergiant Betelgeuse. The star Betelgeuse has a surface temperature of 3000 Kelvin and is 600 times the diameter of our Sun. If our Sun were that large, we would be inside it. Assume that it radiates like an ideal black body. Part A. If Betelgeuse were to radiate all of its energy at the peak intensity wavelength, how many photons per second would it radiate? And part B, find the ratio of the power radiated by Betelgeuse to the power radiated by our Sun, whose surface temperature is 5800 Kelvin. Okay, so peak intensity wavelength. So we have for an ideal black body Wien's displacement law, which states that the peak intensity wavelength lambda max times the temperature T is a constant. Wien's constant 2.9 times 10 to minus 3 meter Kelvin. So we can calculate the maximum wavelength for this temperature, 3000 Kelvin for Betelgeuse. That is 2.9 10 to minus 3 divided by 3000 Kelvin, which gives us a maximum intensity wavelength 9.67 times 10 to minus 7 meters. Now, as for the power radiated by an ideal black body, we have Stefan's law. The radiated power is Stefan's constant sigma, surface area A, the surface temperature T to the fourth power. Emissivity is equal to 1 for an ideal black body. And this is equal to, since it's power, that's the number of photons radiated per second, where each photon carries an energy, E photon, and I call the number of photons radiated per second to be capital N. So we can see that capital N is Stefan's power, sigma A, surface temperature to the fourth power, divided by Hc divided by lambda, but here we're looking at the maximum intensity wavelength. So this gives us the number of photons emitted per second, sigma A, t to the fourth power, maximum intensity wavelength, divided by Planck's constant times the speed of light, c. Now, we know Planck's constant, 5.67 10 to minus 8 watts per meter square, Kelvin to the fourth power, Stefan's constant. And the radius of the Sun, we know, 6.96 10 to 8 meters. Now, what's the surface area of Betelgeuse? The surface area, since we have approximately a sphere, the sphere surface area is 4 pi r squared. That is 4 pi times, since it's 600 times the radius of the Sun, or diameter of the Sun, 600 times the Sun radius squared. That would be the surface area. Now we can calculate the number of photons emitted per second, sigma, Stefan's constant, 5.67 times 10 to minus 8, area 4 pi, 600 times the radius of the Sun, 6.96 10 to 8 meters parentheses squared. The surface temperature to the fourth power, 3000 to the fourth power, multiplied by maximum intensity wavelength, 9.67 10 to minus 7, and this is to be divided by Planck's constant times the speed of light, 6.63 times 10 to minus 34 joule seconds times 3 times 10 to 8. So we find the number of photons emitted per second, 4.9 times 10 to 49 photons per second. That's the answer to part A. We calculated how many photons per second it radiates. And part B, ratio of the power radiated by Betelgeuse to that of our sun. They have different temperatures. Now, Stefan's law tells me that the power radiated by Betelgeuse divided by the power radiated by the sun is the intensity of the radiated by Betelgeuse times the area, surface area of Betelgeuse, intensity radiated by the sun times the surface area of the sun. This is, Stefan's law tells me it's proportional to surface temperature to the fourth power, and it's proportional to the surface area 4 pi radius of Betelgeuse square divided by surface temperature of the sun to the fourth power 4 pi radius of the sun squared. So that tells me this is 3000 divided by surface temperature of Betelgeuse divided by surface temperature of the sun, 5800 to the fourth power, and the fraction of the radii is 600, so it's 600 times the radius of the sun, 600 squared. So that gives me the power radiated by Betelgeuse divided by power radiated by the sun to be 2.6 times 10 to 4. So that's the answer to part B. So in part A, we've used Wien's displacement law to calculate the wavelength for the maximum intensity. And then the Stefan's law tells me the power radiated, which is the energy per second. The total energy is number of photons times energy carried by each photon per second, is Stefan's constant surface area, surface temperature to the fourth power. For an ideal black body, emissivity is 1. So this tells me that the number of photons radiated per second is sigma AT to the fourth power lambda max over hc, because the photon energy is hc over lambda. And substituting the constants here and noting that I have 600 times the radius of the sun for radius of Betelgeuse, I can calculate the number of photons per second. The ratio of the powers radiated is the ratio of the surface temperatures to the fourth power ratio of the radii square, and that gives me 2.6 10 to 4.